Okay, so today we're going to be talking about exponential and logarithmic applications. And like I said, I will be relying on the Desmos Scientific Calculator to show you how to do these calculations. So if you want to use the same calculator I'm using, I recommend opening it up, desmos.com/scientific. Alright, so scientists and researchers often use alternate forms of growth and decay models. Below are two such formulas. This is a variant of P times e to the RT formula introduced in lesson 710. So we have continuous exponential growth and continuous exponential decay. So you only use these particular formulas when we're dealing with continuous growth and decay, okay? All right, so looking at the first question, it says in 2007, the population of the state of Georgia was 9.36 million people. In 2000, it was 8.18 million. Determine the value of K and Georgia's relative rate of growth. So Y represents the final amount of substance, A represents the original amount, E is Euler's number, K is the constant rate of continuous growth or decay. If it's negative, it's decay, and if it is decay, you need to make it negative. And then time in years. So we're going to go ahead and identify each one of these items. I forgot to pull my Iterate tablet up, so give me a second. No. So I usually start with T, which is time in years that has passed. How many years have passed?
7.
Good. So your T is going to be 7. A is going to be the original amount. So that can be population, it can be a substance, many different things. In this case, what is our original amount? Good, 8.18. That's how much of the population we started with. Y is the final amount, which is what? Good, 9.36. Okay. So as you can see here, we have Y, A, and T. So we can only be missing one variable, and that's true, we are only missing K. So we're going to go ahead and solve for K by plugging into the formula. And remember, E is not a variable. Okay. So this is going to be 9.36. I'll zoom in so you can see it a little better now. Is equal to 8.18 times e to the power of 7 times k. So does everybody see how I plugged in for t, a, and y? And then my goal is to get e by itself, so I'm going to divide both sides by 8.18. And if I do that math, it's probably going to give me a pretty gross number that I don't want to deal with right now, so let's see what it gives me. Yeah, so it gives me a number that I can't round, so I'm going to leave it that way in the calculator. So what I'll do on Desmos is I'll type that in, and then I'm going to add to this as I go through the problem. So I now have this over this is equal to e to the 7k. Now we know that when we have to solve for a variable in an exponent, we have to take the what of both sides. The basis of the whole entire unit, module. Starts with an L. Good. ln, or in this case ln because it's a natural log, right? Why would we use the natural log as opposed to the regular log here? Anyone know? There's some key giveaway in this. Yes? Very good. There's an e. So if there's an e, you want to take the natural log. So we're going to take the natural log of both sides. And then what can we do with this exponent out front? Yeah. Well, I meant to say, you know what I meant. Okay. Good. And then we end up with 7k times ln of e. What did we learn about ln of e yesterday? It's 1, so do I need to write it here anymore? No, I can get rid of it because it doesn't do anything. And then the last step to get k by itself is just to divide by 7, right? So now I can find what k is approximately by putting all of this in the calculator, okay? So if I have my Desmos calculator up, okay, right here, I'm going to take the ln of this. So this calculator is easy because you can type into it. And then I'm going to divide this whole thing by 7, right? So that's the calculation I'm trying to do. So I type it into my Desmos Scientific Calculator, and it gives me about 0.02. Okay. So if I want to convert this rate into a percentage, what would it be? 2%. Okay. Okay. So we just found the value of k. So let's say we wanted to rewrite this formula so that we have the general formula for population growth in the state of Georgia. Well, I'm going to write it over here because we're going to use it for this next problem. They want us to use the information we just came up with from part A to figure out what Georgia's population will be or when it will reach 12 million people. So my formula is y equals 8.18, right, because that's how much we started with, and then it's going to be e to the power of, well, we don't know time yet, so we're trying to figure that out, right? So it would just be whatever the rate is to the power of t. So when you want to write a general formula that works for everything, you always want to leave y and t empty, because those are like your x and your y. You know, we have like quadratic formula and we have all of those like linear equations. We leave x and y blank. We don't fill in for them. Okay. So now we have our general formula, so we can use this formula to determine whatever they're looking for. So determine when Georgia's population. When you hear the word when, what does that mean? Time. So we're trying to find time. And this right here, 12 million people, will represent the final amount of the substance or the group of whatever we're looking at, right? So we're going to be plugging in 12 million into y. But here's the thing. This was 8.18 million. So am I going to plug in 12 or am I going to plug in 12 with all the zeros? So if I did that, I would have to convert this to millions. So I'm going to leave it as just 12, right? Because I'm keeping everything in millions. So it's okay to do that. Divide by 8.18. This cancels out and leaves me with 12 over 8.18 is equal to e to the power of 0.02 times t. If you want to get rid of an exponent, a variable and an exponent, what do we take of both sides? The ln. Natural log. What's going to happen with this exponent here? Out front. What is ln of e? So I can finish it off by just dividing. So t is approximately equal to, I'm going to have to type this in my calculator to figure that out. So if I scale this Desmos down, I might be able to fit it on the same screen. We'll see. So we have this right here. So all I'm going to do is I'm going to change the numbers. There's no need for me to delete all of this. So I changed it to 12, and I changed this to 0.02, right? Oops, I don't know what happened there. Like that. And that gives me approximately 19, right? So that's going to be about 19 years, a little over 19 years. You could say 19.2 years. Any questions about that one? Okay. Same idea as what we've been doing, just a little bit different. All right. So number 2 says, during the 19th century, rabbits were brought to Australia. Since the rabbits had no natural enemies on their continent, their population increased rapidly. Suppose there were 65,000 rabbits in Australia in 1865 and 2,500,000 in 1867. Write an exponential function that models the rabbit population in Australia. Okay. So we have our formula that we used on the last one. And this is population growth, right? So I use the positive exponent, okay, because it's growth. So first thing we want to figure out is time. How many years have passed in this problem? 2 years. Good. How much did the population start with? Good. And what is the end population result as we're looking at it? Good, 2,500,000. Okay. So we have 3 variables. That's what you want. So you can plug in to solve for the 4th. That's always what's going to happen. You just may be solving for different variables each time. So I'm going to take my formula and I'm going to be plugging into it. So y is this is equal to this times e to the power of 2k, right? 2 times k, because we're trying to solve for k, we don't know what k is. What's going to be the first step in solving this? Good, divide by the 65,000. So the good news in this one is, because who wants to keep writing those big numbers? I'm pretty sure this one simplifies to something that isn't so bad. Making sure I'm putting in enough zeros. That's 5 zeros, yeah? Divided by 65. 1, 2, 3. Oh, it doesn't simplify so nicely. But we could technically cancel out zeros, but I don't want to get too complicated, so let's just leave it as is. So what I did in my calculator was I just typed this in, so I can add to that as I go through the problem. Okay. So I end up with all of this is equal to e to the 2k. What do we have to do next? Good. Take the ln of both sides. I'm going to write 2.5 million just to save time. And you're going to see what always happens here. Same thing. The exponent comes out front. What's going to happen with the ln of e? It's going to go away because it's just 1. So once you get the hang of it, you can just say this. Okay, because the ln of e goes away, I don't need to write it. And then what's my last step to get k by itself? Divide. Okay, so in my calculator, I pull it over here. I'm going to take the ln of this, and then I'm going to divide it by 2. And that gives me 1.82. Okay, 1.82. So that's a pretty big growth rate. So now they want us to write an exponential function that models the rabbit population. So what you then do is you rewrite the equation, but you leave the y and the t out of it. So you only put in the a and the k. Okay. So the formula is going to be y equals 65,000 times e to the power of 1.82 times t. So this is the formula. Now this formula can now be used to model rabbit population at any time period. So I could look 100 years in the future, use this formula to come up with that answer. Okay. So we're most likely going to use that formula right over here in the next problem. So it says, assume the rabbit population to continue to grow at that rate. Estimate the rabbit population in 1872. So if we think of when this formula is based off of, the year 1865, how many years have passed since 1865 to get to 1872? 7 years, right? So you always use whatever the original time is, and then how many years have passed. Okay. So our formula is this one. We're going to use this formula. And I'm going to plug in 7 in for t. And then this one's a little bit easier to calculate because you don't have to solve for any exponent here. Does everybody see what I mean by don't have to solve for an exponent? There's no variable in the exponent. So all I have to do is type this in into my calculator. It's going to look something like this. Okay, it's pretty big. Pretty large number, as you can see. So you all know how to use scientific notation, how that works? Okay. So if they're saying it's about 2.2 times 10 to the 10 power, how you can approximate that is, well, I can use the more exact number if I wanted to, but this is approximately 22.2 billion. Okay. So, yeah. See the problem with invasive species? Putting random species in different spots where they aren't supposed to be.
Didn't they also try to import foxes to eat them, which just made it worse?
I think that something like that happened in Australia. I know they did that in another country, and then it like killed a bunch of the other wildlife. Yeah, it's kind of scary. When we try to get involved in these things, it's not good. All right, does anyone have any questions about this? Yeah, it's a little bit, but if you use this calculator, because I'm like writing out every step, but you can use the calculator and just type it in as you go on this too. It kind of helps.
For our homework, are we able to like skip the step where it evolves to the fraction?
Yeah, so
Just go straight into the fraction.
as long as you know what to do there, that's fine. Yeah. So I'm just showing you everything so everybody understands. So the amount of time required for some substance, radioactive, biological, chemical, to decay to its original amount is its half-life, half of its original amount. If A is the initial amount of the substance, then the amount y that remains after the substance half-life can be represented by 1/2 A or 0.5 A. This information can be used to manipulate the continuous exponential growth and decay functions in order to find a constant rate of continuous growth or continuous decay. Alright, so let's talk about how we do this. So the first question says, a half-life of carbon-14 is 5,730 years. Determine the value of K in the decay equation for carbon-14. So, I know I'm going to be working with the same formula we've been using. Okay. So it's y equals, so I'll make sure I have it completely right, A times e to the power of kt. Okay, so we're now going to plug into this formula. So whenever you see that you're doing a half-life problem, okay, you see that word half-life, your y is always going to be 1/2 or 0.5 A right off the bat. Okay, you see that? Anytime you're doing half-life, your y is going to be 0.5 A. Now we want to figure out the rest of the information regarding this particular problem. So in this case, let's determine everything else that we need to know. We don't know what the initial amount of carbon is, right? But we do know that time is 5,730 years, okay? So let's plug this into the formula. You're going to see what happens. Alright, so does everyone see what happened there? I plugged in for y and I plugged in for t. So you're going to see why you don't need to know A in this problem. What's going to happen since I have A on both sides? They're going to cancel out because if I divide both sides by A, the A's are both going to go away. So you don't even need to worry about A in this one. So it's just going to become 0.5 equals e to the power of 5,700 and whatever. Okay, what would we do next to solve this? Good. ln on both sides. And are you starting to get the hang of what's going to happen at this stage? Isn't this just going to become ln of 0.5 is equal to whatever the exponent is? So everybody see how I got that? Because you bring out the exponent out front, times ln of e is 1, and then my last step is to divide by that gives me k is approximately equal to, and then we have ln of 0.5 divided by 5, 9, there's whatever, and that gives me negative 0.0000121. Did we expect the amount to be negative here for k? Why did we expect it to be negative? It's decaying. And did we expect it to be a really slow growth rate? Or decay rate, rather? Yeah, because it took 5,730 years. Okay, so the rate is very, very slow. It's not happening overnight. This is over thousands of years. Okay. So the next question. A paleontologist examining the bones of prehistoric animals estimates they contain 2% as much carbon as they would have contained when the animal was alive. How long ago did the animal live? Okay. So in this particular problem, notice a similarity. We're talking about carbon 14 again. Didn't we just determine carbon 14's decay rate? We determined it to be negative 0.000121. Okay. Now that means that the bones, basically, or whatever it is, contains 2% as much as it would have when they were alive. So in this case, your y is going to be 0.02 times their original amount, right? A is the original amount of the animal's mass. 0.02 times A is how much of the mass is left after whatever's happening. Does that make sense? Okay. So now we know K and Y, and we're going to plug into the formula. So that's going to be 0.02 A equals A times e to the power of the rate times t. What's going to happen with the a's on both sides? Good. So you know that if you're not given an a, that you're going to have to use this formula where the a's cancel out in some way. Okay, that's kind of a giveaway. And then I'm going to take the ln on both sides. And when I take the ln over here, I'm just going to be left with the exponent, right? I think I forgot a 0 here. Getting lost track of how many zeros I have going on there. Divide. Okay. So I type this in the calculator. And that gives me approximately this number. So this formula tells me that the specimen of the animal that they found the bones for lived 32,333 years ago. Yeah, a long time. All right. I'm going to stop.